Hi, everybody. My name is Sarah Klapoff, and this semester I worked with Dr. Valerie King, and we looked at alpha stretch probabilistic tree embeddings and their applications in physics. So I'm doing a combined degree in physics and computer science, and throughout my degree, I've been really lucky to get to see some of the astronomy work that people at UVic are doing. And so I've really enjoyed that. It's been a favorite part of my degree. And so for this project, I wanted to look at some PTE algorithms, and then I wanted to look at applying those algorithms to problems in physics and astronomy. So if we have a graph, often with a lot of edges, a lot of information, but we just have one specific property that we want to inquire about, we can build a tree representation of the graph that's a little bit simpler, but will still preserve that property. If we can then solve the problem on that tree, it will give us an approximation to the solution on the graph. So the property that you want to preserve will dictate how you build this tree. But if we want to look at the expected distance between any two pairs of nodes on a graph, then we want to make an alpha stretch probabilistic tree embedding, where alpha is the stretch. And that tells us how close our approximation is, or in other words, how much the distance between those two nodes changes or stretches in the tree representation. So in other words, if we want to know the expected distance between two nodes on a graph, we can look at the distance between those two nodes on a tree, and that will tell us within a factor of alpha how close those nodes actually are. And so we took a really in-depth look at the 2004 work from Fakcharanfal, Rao, and Talwar, or the FRT algorithm, which says that for any graph, there exists a PTE with stretch O of log n, and that this is a tight bound. So we cannot get any closer than O of log n. And then we also looked at some applications in physics. So one of those applications was modeling the Biot bulk network design problem. And I looked at modeling that around processing data from a large astronomical survey. Another application that I looked at was approximate distance oracles. Those are compact storage data structures that answer pairwise distance queries. And so PTEs can be used to speed up oracle construction. And then those oracles can answer questions regarding the distance between 2 points in a simulation, such as this one of a galaxy merger, or in other physical systems.